Okay, so let's have a look at the specific tasks we can study in machine learning. So we can look at the first task on supervised learning about classifications. So what is supervised learning? Normally, supervised learning assumes we can have some training data with knowing labels for some of the data instances. And with this kinds of knowing data with knowing labels, we can train a model. And then we can further apply the model to some data instances with unknowing labels, right, for testing. And based on performance, we can further do the evaluations. So you can see, in the supervised learning, we have several stages. So we have training. Training denotes we learn a model with training data set. And we also have the testing. Testing means we test a model with some unseen testing data set. We also have evaluation. Evaluation means we measure the model performance based on testing set. So here the part 9. Let's assume we have a training data. In the training data, we see the data, right? We know the data with the labels. Like given an image of a dog, we know it's an image about a dog. We know the label, right? And based on training data, we can train a model. We can train a machine learning model, which will be a mapping, right? And training the model means we want to learn the model parameters. Because in most of the machine learning models, we will have the parameters to be learned. And by learning the parameters, we will be able to get a model. So the model means the machine learning algorithm together with learned parameters. And together we define a model. Okay, so when we're talking about model, actually we denote the machine learning algorithm together with learned parameters. And then we can apply the model to some data instances in the testing set with unseen labels. Now we train a machine learning model which can recognize dogs from images. And we can apply the model to a testing set with many images, but we don't know it is about dog or about cat. Then we can apply the model to the testing set, right, to the images to see they are about dog or they are about cat, right? We can get some results. So we can compare the prediction results by the model on the testing set as well as the ground truth. Ground truth means the true labels of these data instances. We can compare them with the ground truth to do the evaluation, right? Based on some evaluation matrices, we can get the performance of the model on the testing set, right? So what is the evaluation metric? Evaluation metric denotes some measurements to measure the performance of the model. A commonly used evaluation metric is accuracy for classification, right? Accuracy means among all the testing data instances, how many numbers of them are predicted correctly. It defines the accuracy metric, right? And you may wonder, what do we mean by the learning? Learning denoting the optimization of some functions or some objectives. We'll talk about this later. Here we learn the model. In the process, normally we will involve the maximization or minimization of some loss functions or reward functions, right? So by optimizing these functions, we can get the optimal parameter settings for the machine learning algorithm. So this is part 9 for the supervised learning. Normally we will have the training data, we have the testing data, we need to train a model, and we can further evaluate the performance of a model on some testing data set. And then we can further have a look at the supervised learning. So normally we need to require a training data set, right? And we also have a task and an evaluation metric. How can we say we have trained a model? How can we say a computer system has been learning from the dataset? So we can say a computer system is learned from dataset D to perform a task T if after fitting the computer system with D, it performs better on task T as evaluated by the metric M. In other words, by fitting the computer system with data, it helps it to perform task T compared with no learning. If so, then we can say the system has been learning from the data to perform the task, right? So it requires the task, also requires data set as well as the evaluation metric. And how can the supervised learning be successful? Normally we have some assumptions for the data in both the testing set as well as the training set. So the assumption is that the distribution of training data instances is identical to the distribution of testing data instances. including the future unseen data instances. This is a very strong assumption because we mentioned here it is identical to, right? The same as. However, in the real world or in the real practice, such an assumption will be violated in certain sense or in certain degree. If a strong violation of this assumption will result in a very poor performance of the model on the training dataset and the testing dataset. In other words, we train a model on a training dataset whose distribution is very different from the testing set. The model will be useless for the testing set, right? Okay, we have been talking about training set and testing set, right? Then what's the difference between them? So formally, the training set denoting the data set on which we train and fit our model. It usually denoting the currently observed data set. Normally, when we train a model, we have to connect some data set, right? And we also to label the data set with some domain experts. So the training set denoting the labeled data set with domain labels, right? For example, for the image of animals, we know this image is about dog, this image is about cat, this image is about bird. Then they are all labeled when we see them before, right? And what about testing set? Testing set is used only to evaluate the performance of a model. It denotes the future unseen data set. So we train a model on the training set and want to demonstrate this model is useful for future data we never met before, right? And then we can apply the model to the testing set to evaluate the performance of the model. You see the difference, right? It's just like the knowledge we learn, right? For example, we have learned some basic knowledge about the mathematics, about physics before, right? So this what we learned before is like training set. And we also want to apply the knowledge we learned before into some future task, into some future cases. These future cases or problems will be more like the testing set for us, right? It will be similar here for the training set and testing set for the machine learning models. Then how can we get them? There are different cases. In some cases, we have predefined the training set and testing set already. And then we can just train the model with the training set and evaluate the model with the testing set. However, in some cases, we only have one single data set, right? We want to use the data set for both the training and the testing. What we can do here is to do the random sampling of the data set into training set and the testing set. For example, given the complete data set, we can do the random sampling of 70% as the training set and 20% as the testing set, right? This is random sampling. It works very well. However, it is not stable because, given the same complete data set, we can always do the random sampling and result in very different training set and testing set. For example, if we run the same process twice on the same data set, we can get a different training set, different testing set, and we can train different models and do different testing, get different testing results, right? It's not very stable because it's all random. A more reliable process for partition a data set into training set and testing set is via the cross-validation. Given the whole data set, we can partition the data set into 4 portions, for example. We can partition the data set into 4 portions, A, B, C, D, right? Then the question is, which one will be used as a training set, which one will be used as a testing set, right? So for the cross-validation, normally we need to do several fold. Several fold means we need to do this several times. In the first time, we can use this D as a testing set, A, B, C as a training set. Someone may say, can we use A as a testing set? Yes, we can also do so, right? In the second round, we can use A as a testing set, B, C, D as a training set. In the third one, we can use B as a testing set, C, D, A as a training set. In the fourth round, we can use C as a testing set instead. You can see, if we partition the data set into 4 portions, we have to do this process with 4 folds, right? In each fold, we use different portion as a testing set and the remaining as a training set. So this is also normally called K-fold cross-validation. As to the evaluation performance, we need to calculate the average performance in all these K-folds as a final result. So compared with random sampling, this k-fold cross-validation is more reliable and more stable. So for cross-validation, we have to partition the dataset into like several portions. Now, someone may ask how large is this portion or how many portions we can have. It depends on your performance as well as your time constraint. The more portions we have to run this cross-validation with more rounds, right? The time cost will be high. The extreme case will be we can split the complete dataset into n portions. Each portion contains one single data instance, right? And we have to run the process with n rounds. It will be extremely time consuming. This one is also called the leave one out partition of the dataset into training and testing. So in the practice, normally we prefer to do the k-fold cross-validation. For my case, I normally do the 10-fold cross-validation to assign the k to be 10. In other words, we can partition the dataset into 10-fold, and we can run the process with 10 times, and then calculate the average scores on the evaluation. Right? So this is more stable and more reliable.